all. This is Team Sebastian. We're gonna put the way that is not the Nudgegate and I just want to know are two system or function. Global function refers to a technical system or function by a simpler function that can be used to make prediction. A simpler function is usually easier to work with and can be more effective to certain approach. On the other hand, the local approximation is a technique that estimates the behavior of a system around a particular point. This approach is useful, is highly varied, and it is difficult to find a single approximation is often used in numerical analysis, optimization, or learning. Overall, the global and local approximations are both important techniques used in mathematical modeling. The choice of which method to use depends on the specific problem and the nature of the function being approximated. Here is the image which shows the brief explanation of where the global and local approximation fall apart from when we got the points to do. For interaction, the first derivation is like dw by dx whole k equals to 0, where w equals to 1, where k stands from 0 to m. Global approximation. So global approximation is initially divided into two types, which is way up approach and way down approach. So we'll just look at it. What is way up approach and way down approach? So the way up approach is in global approximation start with a small number of simple functions and increase the complexity of the approximation gradually. Simple global functions such as linear or polynomial functions are chosen for approximation. The approach aims to build an accurate approximation over the entire function domain by adding more complex functions if required. The approach is commonly used in numerical analysis for approximating complex functions in simulations, finding a balance between accuracy and computational efficiency. The way down approach. The way down approach in global approximation begins with a large number of complex functions and gradually reduces their number while maintaining an acceptable level of approximation accuracy. This approach simplifies the approximation while minimizing the loss of accuracy by removing functions that contribute little to the overall approximation error. The process continues until the described accuracy level is achieved with the smallest possible number of functions. This approach is often used in optimization and machine learning to approximate or simplify complex functions efficiently. So least square curve approximations. So we're gonna look into where we use these things. So least square methods also called as least square approximations in statics, a method for estimating the true value of some quality based on the consideration of errors in observations or measurements. The method of least squares is a standard approach in regression analysis to approximate the solution of overdetermined systems by minimizing the sum of the squares of the residuals made in the results of each individual equations. Least squares curve approximation. So for this we use control points. So computing control points uses least squares is a common approach in the curve and surface fitting. Control points are used to define the shape of the curve or surface, and least squares is used to find the control points that best fit a set of data points. How are the general steps to compute and control points using least squares? Define a curve or serve equation in terms of control points. Choose first thing, like first we define the curve or simple equation. Second one, initial step of central control points. Like third point, calculate the residual errors between the curve of surface equations and then the data points. Use least square to minimize the residual errors by adjusting the control points. So here are the equations. Cu equals to sigma NIPU, the given thing, where sigma is k equals to 1, where k lies from m minus 1 to mod of qk minus c into uk whole square. where Q naught equals to C naught and Qm equals to C1. So the remaining Qk is approximated in the least square sense. That is the equation which I specified initially. We start with a simple curve to fit the point data, and then we emphasize the resulting curve generally does not pass precisely through. So the equation falls like Rk equals to Qk minus n or no p of uk q naught and minus npk np uk mod of qm, where k lies from 1 to m minus 1. The f simpler equations of all apart like that, which as shown in the slides. Least square approximation. Now we simply the standard technique of linear least squares fitting. To minimize f, we set the derivatives of f with respect to n minus 1 points, p1. So the ith derivative is as shown in the slide. So least square curve approximation matrix equation. We begin by clarifying exactly what we will mean by a best approximate solution to an inconsistent matrix equation where Ax equals to B. Let A be an M cross M matrix, and let's B be a vector in Rm. A least square solution of the matrix equation where Ax equals to B, as I said initially, is a vector of Kx in Rn such that distinct of B of AKX is less than or equals to distance of B of A of X. So what is transformed approximation? Transformed approximation simplifies complex functions by approximating them with a simpler one though suitable transformation. The original function is transformed, approximated with a simpler function, and then transformed back to the original using the inverse transformation. So this technique is useful in engineering, physics, and finance, but may introduce errors and is not always suitable for all functions. So the transform approximate equation falls like as shown in the slide. So linear Taylor series. Taylor expansion is a function isn't of a function is an infinite sum of terms that are expressed in terms of the function's derivatives at a single point. Taylor's theorem is taught in introductory level calculus courses and is one of the central elementary tools in mathematical analysis. So where f of x equals to f of a plus f inverse of a into x minus a plus h1 of x into x minus a, which falls limits of limitation h1 of x equals to 0, where x starts from a. So the right image shows the slope and point. The intersection point is f of a, and the intersection above point is f of x. So least square approximation with n derivatives. This is second topic of the course of our presentation. So least square curve approximation with n derivatives. Find a curve that fits data points using satisfying n derivative conditions. It minimizes the sum of squared differences and solve a polynomial function of certain degree using a system of equations. This method is useful for applications where the behavior of the curve at endpoints is important. So the image in the right side shows the point which we like initially got, or which we consider initially. So where the W1 and W1 to Wn values vary, the point which falls under the domain, which point under the consideration of error approximation, which considers which consider to be the least errors, and then least square approximation with the formulas with the matrix. So R is vector of n minus 1 points, where R equals to the matrix given in the slide, and P equals to P1. P falls from 1 to n minus 1, where U is equals U is considered between U naught to UR, and parameters UK are required, and that is where I is less than or equals to D. So it follows that the initial equation which we discussed in the initial slides. So the above equation, one linear equation is known as is unknown, where P falls from P1 to Pn minus 1, letting I equals to 1 to n minus 1 is a system of n minus 1 equations in n minus 1 unknowns. So n transpose of n into P equals to R, where in the before slide the dependence may be the R is dependent on this vector, where n is n minus 1 into n minus 1 matrix of scalars, and the given matrix is as shown in the slide. So least squares curve approximation with n conditions, the derivations and the curve fitting method. So R is a vector of n minus 1 points, which where initial slide we said R equals to n transpose of n into P. So the matrix is shown in the slide. In order to set up the matrices n and R, a knot vector u equals to u naught to u, and parameters of uk of mod are required. The placements of the knot should reflect the distributions of the uk mod. If d is a positive real number denoted by I equals to integer of d, the largest number, such that the largest integer I less than or equals to d. So in total, we need n plus p plus 2 knots. So by considering the image right side, we let the image let us know what are the points, like what are the knots to be taken into the consideration. So d equals to n plus 1 by n minus 1 into p, which we thought of the points knot initially. So then define the internal plots by I equals to integer of jd, where alpha equals to jd minus 1. So j depends from 1 to n minus p. The above equations guarantee that every known span contains at least one least square curve. So the matrix n can be very large, and most of these is are zeros. In some applications, it is not uncommon for m equals to 1000 and n equals to 100. So here we consider we are just considering m equals to 1000 and n equals to 100 to just to decrease the time span of a work, or like the and the cost efficiency. So the m and n values may depend, it may be into billions or trillions, so that the equation continues for the days, and may even increase the cost of considering the equation. So we are just using the simplest terms to just go ahead. The implementer may want to develop a storage scheme to store only non-zero elements of n. So in the distant sense, the approximation improves as the number of control points increases. However, as the number of control points approaches, the number of data points and unwanted wiggles and shapes can occur. So the three images shows the when the number of control points increases, the number of data point approaches may also be increased, and the region of data point may be decreased when the points are together. What is parameters and knots? Parameters refers to a coefficients of the polynomial function that approximate the curve. The number and the value of parameter depends on the degree of the polynomial used. Using the approximate degree and number of parameters can impact the accuracy and complexity of the approximation, and is determined by the specific applications and desired accuracy level. So knots are the points where the polynomial function changes in direction. The number and location of knots can impact the accuracy and smoothness of the curve. The choice of knots is determined by the specific application and desired level of the accuracy, and can be optimized using techniques such as cross-validation. So the image on the right side, which depends only which shows depicts only the parameters and can the knots, where the knot is like a more near, and the parameter is the area of the point which considered. When performing a least square regression, the choice of parameters and knots depends on the nature of the data and the goals of the analysis. Here are some general guidelines. So what we do in parameters and knots. So parameters, choose the number of parameters based on the complexity of the model and the number of observations. As a rule of thumb, the number of parameters should be smaller than the number of observations. So we are using, like we are now using the right hand thumb rule or left hand thumb rule, which depicts the parameters, which shows the parameters and the number of observations through the directions through the fingers. If the model is too complex, it may overfit the data and perform poorly on new observations. If the model is too simple, it may not capture the underlying patterns in the data. So what's not now initially we discussed about the parameters. Now we're going on to the knots. Knots are used in spline regression to define the segments where the model changes. The choice of knots depends on the nature of the data and the level of smoothness desired. If the data are smooth and do not have many abstract changes, fewer knots may be needed. So whenever the data is like smooth and there are no changes are occurred, the only the fewer knots are required to solve the equations, or show the data points. The data have many abstract changes, more not maybe needed to capture the changes accurately. Here are some specific methods for choosing parameters and nodes. So for like the what to use between parameters and nodes, we have some techniques in which first one is cross validation, splitting the data into training and validation sets, fit the model to the training set, and evaluate the performance on the validation set. So the second one is al- archaic information criterion. AIC is a measure of the goodness of fit of the model that takes into account the number of parameters used. Bayesian information criterion (BIC) is similar to AIC but has a stronger penalty for the number of parameters used. Visual inspection: plot the data and the fitted models for different choices of parameters and nodes. Choosing between parameters and nodes. So initially we got to know 4 points, four different methods where we can choose which are used to help us choose between parameters and nodes. To choose parameters and nodes in least squares curve approximation with n derivatives, the application and desired level of accuracy must be considered. The degree of the polynomial and the number of parameter affects accuracy and complexity, while knots impact curve smoothness. So cross-validation is a useful technique to determine the optimal degree, number of parameters, and knot locations. So ultimately, the goal is to strike a balance between the accuracy and complexity of the model, while ensuring that it accurately represents the underlying data. So what basically control points are? Control points in least curves approximations with n derivatives define the shape of the curve. They are used to construct a spline curve that passes through the control points with certain smoothness properties. The number and location of the control points can affect accuracy and smoothness and are chosen based on the application and desired accuracy. Cross-validation can be used to optimize the number and location of control points and ensure that the curve accurately represent the data. To compute control points in squares curve approximations with n derivatives, a B-spline basic function is commonly used to construct the spline curve. The control points are adjusted to approximate the underlying data with the number and location of control points, optimized using techniques like cross-validation. The goal is to strike a balance between accurately representing the data and minimizing unnecessary complexity in the curve. Ultimately, the resulting curve should accurately represent the data without introducing unnecessary complexity. So set up and solve matrix equation. To set up and solve a matrix equation in least squares curve approximations with n derivatives, a B-spline basis function is defined and used to construct the spline curve that passes through the control points. A set of basis functions is defined to approximate the data, and the linear equations are set up to relate the coefficients of the basis functions to the observed data. And derivatives constraints are incorporated by adding additional linear equations to the matrix equation. Numerical methods such as QR decompositions or similar value decompositions like QR decomposition and SVD so can be used to solve the matrix equations and obtain the coefficients of the basic functions. The matrix equations in least square curve approximations with n derivatives can be expressed as A transpose into A into X equals to A transpose of Y, where A is the matrix of basis functions, X is a vector coefficients, and Y is a vector observed data. So here is an brief simple example of our given data in the right side. So how we how what are the steps involved in solving the equations, like solving this problem? We are gonna just look into it in the next slide. So pseudo algorithms, like which we use, like what are the steps we just simplify and solve the equation. Define the B-spline basic functions and construct the spline curve that passes to the control point. So initially, just construct and spiral curve which pass only through the control points, like what are maybe how many number of control points maybe there. So just consider the equation and then define a set of basic functions to approximate the data. Set up the matrix equation using the basis functions, observe data, and decide n derivatives. Solve the matrix equation using numeral methods such as QR decomposition and SVD, that is singular value decomposition. So this fourth point is like we just gone to the similar point in the previous slide. Obtain the coefficients of the basic functions that define the spiral curve. Use the coefficients to evaluate the spiral curve at any desired point. So these six steps are used to solve the previous, like the example in the previous slide. So the following set points of 1, comma 3, 2, comma 4, 5, comma 6, 6, comma 10. So initially, first we write the spiral equation, and then we approximate the data, and then we convert into matrix, and then we used QR and SVD equations to solve that, and with the matrix equation of least curve, which is like A transpose of T, A transpose of A into X equals to A transpose of Y. So we use this similar form, like similar equation to solve the given obtained matrix, and then solve the question. So the above algorithm can be further optimized or modified based on the specific implementation requirements or constraints. So what are control points? We just discussed, and different control points. It seems like we may have one, two, like three different control points for this given curve. So we are just considering a group of control points into three categories. So initially the we consider only five control points, which we named as few control points. So in this, we use only five control points and a degree of 3 line basis functions. With 8 knots, we can obtain a smooth spiral curve that approximate the data by solving the matrix equation for the coefficients. So more control points with 10 points, the spiral curve can capture more complex patterns in the data by defining a set of basic functions with more knots, resulting in the larger matrix equation to solve. Even more control points. Like as I said, we have 3 points. We are just considering three different categories in which few control points are one is few control points, second one is more control, and third one is even more control points. In the few, we are considering only five. In the more control, we are considering 10. In the even more control points, we are considering 20. So for more control points with 10 control points, the spiral curve can capture more complex patterns in the data by defining a set of basic functions with more knots, resulting in the larger matrix equation to solve. So when the control points is increased, the matrix equation will be like the larger one, because the number of control points is more. So the values are from like 1 to n minus 1. It may be it initially, so for the first one we consider from 1 to 5. So it's like 1, 2, 3, 4, 5. Only the equation is only contains only five categories, but here we go with 10 categories, and for the third one we go with 20 categories, which is more difficult and more cost efficient, not efficient actually, more cost consuming thing. So these are the three types, and from here Sindhu will continue the presentation. Thank you. Before concluding the presentation, so I just want to conclude one point. So in here, yeah, for the equation, more of sigma k falls from 1 to m minus 1, qk minus c of uk mod of whole square. We only consider whole square here because the denominator, all for the mod equation, the denominator always consider the distance. So we never happen to fall in between cubes and whole power 4s. Even though we consider whatever may be the whole power thing, we are this is a topic of least square curve approximation. So we only we like we uh, we consider our equation, or we just resolve our equation to the squares. Even though it's cube, we'll just split into we'll make it to as square, and we initially split the equation and we directly split into squares. So here I just want to just want to give a brief note about that. So from here, my simple and that's it for my side. Thank you.
Hello everyone. So today I'm going to be discussing about weighted and constrained least square curve fitting. So weighted least square curve fitting is a type of regression analysis that minimizes the sum of the squared weighted residuals between the observed data and the predicted values from a given model. The weighted factor is usually determined by the inverse variance of each data point, which gives more weight to data points with smaller variances and less weight to data points with larger variances. Constrained least square curve fitting is a type of regression analysis that imposes constraints on a fitted parameters of a given model. So these constraints can be in the form of upper or lower bounds, equality or inequality constraints, or linear or nonlinear constraints. Both of these techniques combines to simultaneously handle data with heteroscedastic error and impose constraints on the fitted parameter of the model. This is very general and weighted constraint least square curve fitting method, and it's a non-uniform basis spline adaptation of an algorithm by Smith and others. So here let qi, comma I is equal to 0 till r be the points to be approximated, and let di of j, comma j is equal to 0 till s be the set of derivatives. So we divide the qi and di of j into unconstrained and constrained sets. Um, q power u base I of 0 till q power u base I of ru and d power u base I of 0 till d power u base I of su are the unconstrained items, and q power c base I of 0 till q power c base I of rc and d power c base I of 0 till d power c base I of sc are the constrained items. Here r is equal to ru plus rc plus 1 and s is equal to su plus sc plus 1. We also allow a positive weight to be assigned to each unconstrained item. Here, if you look at the picture, it is a unconstrained fit with all weights equal to 1 and the curve does not pass through the endpoints. The weights allow additional influence over the tightness of the approximation to each data item relative to its neighbors. Here, W per Q base I and W per D base I is equal to 1, which is by default. Increasing the weight increases the tightness of the approximation to that item, whereas decreasing it loosens the approximation to that item. Now let mu is equal to ru plus su plus 1 and mc is equal to rc plus sc plus 1. Approximate the unconstrained data in the least squares sense and interpolate the constrained data with the pth degree non-rational curve with n plus 1 control points. The next algorithm requires that MC less than N, MC plus N less than MU plus 1. Now let SK, where K is equal to 0 till MU, be the kth unconstrained data item. Here, if we look at the picture, it is unconstrained fit, but with the weights. The weights are W per Q base 4 is equal to W per Q base 5 and W per Q base 6 and 7, which are equal to 0, and the curve does not pass through the endpoints. Here, Tk, where k is equal to 0 till mc, be the kth constrained data item, and wk, where k is equal to 0 till mu, be the kth weight. Here, we define the following vectors or matrices, where S is a vector with mu plus 1 elements, and T is a vector with mc plus 1 elements, and W is a diagonal matrix with the Wk on the diagonal, and P is a vector of n plus 1 unknown control points, where n is a parameter value corresponding to an unconstrained data item. and m is a parameter value corresponding to a constrained data item. Determining the curve is basically a constraint minimization problem involving n plus 1 unknowns and mc plus 1 constraints. The standard solution is to use Lagrange multipliers, introducing mc plus 1 additional unknowns and Lagrange multipliers, obtaining n plus mu plus 2 into n plus mc plus 2 system of equations. And in the picture, it has weights of 100 and the curve does not pass through the endpoints. Here, the unconstrained equations are NP, which is equal to S, and the constrained equations are MP, which is equal to T. And by using Lagrange multipliers, we want to minimize the expression. And by differentiating and setting equal to 0 yields, we get MP minus T is equal to 0. And by transposing and factoring 2 out of A yields, we get MP is equal to 2. And in partitioning matrix form and by solving the equation for P, we get P is equal to N transpose W N whole transpose and N transpose NS minus N transpose of W N whole transpose and into M transpose A. And by solving for A and P by multiplying M on both sides and substituting, we'll get the below equation. So this is the algorithm where the algorithm name is WC least square curve, and we have different parameters like Q, R, WQ, and etc. And we have different inputs that are given, and the expected output is U and P. So initially we have given values for RU and RC, which are equal to -1, and it runs through the loop where we have a condition in which WQ of I, if WQ of I is greater than 0.0, then RU gets incremented by 1, or else RC plus RC gets incremented by 1. And SU and SC are initialized to -1, and again it runs through the for loop wherein if WD of J is greater than 0.0, then SU will get incremented by 1, or else SC will get incremented by 1. Here MU is equal to RU plus SU plus 1 and MC is equal to RC plus SC plus 1. If MC is greater than or equal to N or MC plus N greater than or equal to MU plus 1, basically if any of that condition is true, then it will give us error. And after that, compute and load parameters up into UB array, and then compute and load the knots into U array. And then setting up arrays N, W, S, T, and M. Initially, J is equal to 0, MU2 is equal to 0, and MC2 is also equal to 0. And it runs through the loop, and we have some functions, find span basis function, and then their basis function. Initially, the flag is set to 0, but if I is equal to I of j, then flag sets to 1. And we also have unconstrained point, constraint point, and derivative at this point, and constraint derivative. And then after that, it computes the matrices N transpose of Wn and then N transpose Ws, and compute the inverse of N transpose Wn using forward backward method. Do matrix operations to get M inverse of N transpose Wn into Mt and M inverse of N transpose Wn into N transpose Ws minus T. So by using Lagrange multipliers, load into A array and then compute P. And if you look at the picture over here, it has unconstrained fit with weight, like every weight is equal to 100 and the curve is not passing through the endpoints. So these are basically pictures, but in the first one, we can see that a constraint curve fit, a point constraints are marked by squares, tangent constraints are shown by arrows, and all the weights are 1. Whereas the second picture, it is similar to the first one, but with the weights. The weights are equal to 100. And if you see the third one, it is a constrained curve fit. A point constraints are marked by squares. Tangent constraints are shown by arrows, and all the weights are 1. Whereas the fourth picture is similar to the third one, but it has weights. W per q base 4 is equal to 50 and W per q base 16 is equal to 20. Next, we have least square surface fitting. So this is much more complex than of curves. So let qk comma l k is equal to 0 till r and l is equal to 0 till s be the r plus 1 into s plus 1 set of points to be approximated with n plus 1 into n plus 1 control points. So like in global surface interpolation, we try to fit curves across the data in one direction and then fit curves through the resulting control points across the other direction. So the picture is a data set for surface approximation. Next, we have algorithm. This algorithm interpolates the corner points and approximate remaining set of points. It uses repeated least square curve fits like we deduced in above equations in least square curve approximation, where Rk is equal to Qk minus N naught comma P into Uk into Q naught minus N base N comma P into Uk into Qm, where K is equal to 1 till M minus 1, and we get the equation wherein we get R value. And it fits the S plus 1 rows of data first, storing the resulting control points in local array, then fits the N plus 1 into M plus 1 surface control points. And if we see the picture over here, the first one is surface approximation, where a least square surface fits with a degree 2 and 3, surface using a 5 into 6 control net. And the second picture shows the error surface, wherein error measured at each data point. It can also done by fitting R plus 1 columns first and then fit across the resulting M plus 1 rows of control points. We don't know which approach will yield the best fit for a particular set of data. And if we compare, the matrices n transpose n and n only have to be computed once for each direction. LU decomposition of n transpose n is only done once for each direction. Variables are local arrays nu and nt into nu for u direction fits and nv and nt into nv for the v direction fits. The vector r is stored in ru. And the picture, the first one is a least square surface with a degree 2 and 3. Surface using a 8 by 8 control net. Here, quality of approximation is much better than 5 by 6 control net. And the second one is, of course, error surface, which has error measured data points. And these are the pictures. The first one is data set for surface approximation, and the second one is surface interpolation points shown in the above figure. Next, we have approximation to within a tolerance. The first one is curve approximation with error control. There is a problem of approximating data with some user-specified error bounds E. Iterative methods either start with few control points fit, check derivatives, and some add control points can be, say, as type 1, or they can start with many control points, fit, check deviation, and discard control points can be called as type 2. Here we can see the picture, which has error points. To degree how nicely a curve can approximate the given statistics polygon, the concept of blunder distance is used. The blunder's distance is a gap among a data point and its corresponding point at the curve. Thus, if the sum of these errors distance is minimized, the curve ought to observe the shape of the information polygon carefully. A curve received this way is referred to as an approximation curve. So here, if we see in the picture, it shows the affected domain, the points till 2 and 6, and it has n5 and 3. Next, we have general strategy. A type 1 curve approximation method can proceed as follows. First, start with p plus 1 control points, which is the minimum, and then fit a curve using RK or algorithm A9.6 if interior constraints are desired. After each fit, use maximum distance measure equation to check if the curve deviation is less than E. A record is maintained for each knot span, indicating whether or not it has converged. A span uj and a wj plus 1 has converged if max distance equation is satisfied for all k such that uk belongs to uj and 4j plus 1. After each fit and subsequent deviation check, a knot is added at the midpoint of each non-convergent span and adding control points. This algorithm must deal with the case in which a span can become empty as nodes are added. The span contains no UK and producing a singular system of equation in the fitted step. A type 1 surface approximation method can be implemented in a similar fashion with an efficiency improvement. During the deviation check, determine the row LO and column KO which have the greatest number of points with deviations greater than E. Then extract isoparametric curve CUN into V and CU of V and independently approximate them to within E. This yields new knot vectors U and V to use for the next surface fit. Using this method, usually only a few surface fits and subsequent deviation checks are required. Now develop a type 2 curve approximation method which combines least square fitting with the knot removal techniques. And so next we have error measures. After removal of C dash of U, which differs from C of U, Tiller derives error bound for two cases. Assume P plus S mod 2 is equal to 0, set K is equal to P plus S by 2. And we'll get BR is equal to P base R minus K minus AR minus K into P power 1 base R minus K plus 1 minus 1 minus A base R minus K into P power 1 base R minus K minus 1, where A base R minus K is equal to U base R minus UR minus K by UR minus K, K plus P plus 1 minus UR minus K. And then we'll get the following equations. Now let Qx be a set of points and Uk the associated set of parameters. Denote by Ex a set of errors associated with the points and let E be the maximum error bound. Given a curve CU with the property that the max norm deviation of each Q from CU is less than or equal to EK, algorithm A9.9 removes as many knots as possible from CU while maintaining EK less than E for all K. It also updates the EX, that is, it accumulates the error. Output is a new curve represented by N, U, and P. The algorithm maintains two lists, the knot removal error BR for each distinct interior knot, and for each basis function Ni of U, the range of indices representing the parameters UK which fall within the domain of the function. Next, we have advantages of linear curve. Geometric characteristics in here in the data tend to be captured at the appropriate stage. If the data is known to be smooth, then algorithm A9.10 can be started at degree 2, which is quadratic interpolation before entering the for loop. The evolving curve tends to settle into a natural parameterization. A general rule when globally fitting large number of points is that the higher the degree and the more knots, the worse the wiggle. Algorithm 9.10 reduces the number of knot spans as it increases the degree, thereby tending to decrease wiggle in the final curve. Next, we have curve approximation with error control. Curve fitting is one of the maximum powerful and maximum widely used evaluation gear in Origin. Curve fitting examines the connection among one or greater predictors and the responsible variable, which is dependent variable, with the purpose of defining a pleasant in shape version of the connection. So the below figure shows the parameterization of this curve along with the control polygon. And the mix of double and single knots is apparent by the alternating touching and non-touching polygon legs. And this is the example of cubic curve approximation with E is equal to 8 by 100. The max normal error bound E is guaranteed in the knot removal steps of algorithm A9.10. The error resulting from the least squares fit is guaranteed to be less than or equal to the error in the previous not removed curve in the least squares sense.
Good afternoon. I'm Nachikeet Joshi, and I'm going to take the topic continue from surface approximation with error control. Surface approximation with error control refers to a technique used in geometric modeling to generate an approximate surface representation of a 3D object while controlling the maximum error introduced in the process. The goal of the surface approximation is to simplify complex 3D models by representing them with smaller number of primitives such as triangles, quadrilaterals, or any other type of shapes that are easier and faster to render. However, simplification can lead to loss of detail and introduce errors that may be noticeable in the final rendered image. Surface approximation with error. Figure 1 in this shows the data set to be approximated. Figure 2 depicts the surface that is obtained by using e is equal to 0 and degree 2, 2. Increasing e to 1 by 2 yields the surface in figure 3. After further increasing e to 1 yields the surface depicted in figure 4. Surface obtained by degree 3, 3 approximating using e is equal to 1 is shown in figure 5. As you can see, there is slight loss in detail when compared to the first image and the last image. Surface approximation with error control uses algorithm that aims to minimize the error introduced during the simplification process. These algorithms typically involve iterative refinement of the approximated surface until the error falls below a predetermined threshold. One common approach to surface approximation with error control is the use of adaptive subdivision algorithms, such as loop subdivision algorithm that recursively refines the mesh until a desired level of detail is achieved while keeping the error within acceptable limits. Loop subdivision algorithm. The loop subdivision algorithm is a mesh smoothing and refinement algorithm used in geometric modeling. It was proposed by Charles Loop in 1987 and has since become a popular method for generating smooth surfaces from coarse meshes. The basic idea behind the loop subdivision algorithm is to iteratively refine a core mesh by adding new vertices and edges while maintaining the overall shape of the original mesh. Another approach is to use error metrics to guide the simplification process, such as mean curvature error or the Hatzroff distance error. These metrics quantify the difference between the original surface and the approximated surface, and they can be used to control the degree of simplification applied to different parts of the model. Curve approximation with data smoothing. Curve approximation with data smoothing is a technique used to create a curve that closely approximates a set of data points while also reducing noise and other irregularities in the data. As you can see in figure 1 and 2, after curve approximation and using data smoothing, we get the curve smoother. Curve approximation, we find that the virtual material relaxes extra strongly to excessive frequency adjustments in data, which may be used for smoothing of records by means of approximating transferring common and low bypass filters in 1D datasets. The rest and minimization becomes home of the version allow that spatial computation of B-spline curves in two-dimensional datasets. Both clamped and unclamped spine curves of open and closed shapes may be represented, and the degree of spine-line curvature corresponds to the rest time of the cloth. Curve approximation with data smoothing methods. There are several methods for curve approximation with data smoothing. Some of them are moving average. This method involves taking the average of certain number of data points, moving that window across the dataset, and replacing each point with the average of the points in the window. This can help to reduce noise and other fluctuations that are present in the data. Polynomial regression. This method involves filtering a polynomial function to the data points. The degree of polynomial determines the degree of approximation. This can be useful method for approximating complex curves. Spine lines. Spine lines are a piecewise function that is used to approximate a curve by fitting a series of polynomial functions to different segments of the data. This method can provide a good approximation of the data while also reducing noise and other irregularities. Local curve approximation. Let Q naught Q1 till Qm be E. Here we give two examples of local curve approximation. The first produces a rational quadratic B spline curve, and the second produces a non-rational cubic B spline curve. In both cases, the curves are G continuous by construction, and they can be made C continuous, but this is not recommended for the quadratic case because it can produce very poor parameterizations. The quadratic curve fits planar data, while the cubic curve fits arbitrary three-dimensional data. A good approximation algorithm attempts to generate a few segments as possible. One way to do this is let Ks is equal to 0, Then find the largest ke such that it is lesser than m, and q of ks to q of ke can fit with tolerance e by 1 pth degree. And this is continued to find largest ke that is less than m and where ks is equal to m. This is achieved by initializing ke to ks plus kmax at the start of each search. Ke minus ks is less than or equal to kmax. For a fixed tolerance, a smaller kmax is accurate. If m is large compared to e, then average number of points approximated with each segment is small. So algorithm is more efficient if kmax is smaller than m. Fit with conic and fit with cubic respectively are developed to fit the points qks to qke to within the tolerance E with a conic or cubic segment respectively. If the fit is successful, the calling routine either accepts the segment or it increases ke and calls the fit routine again to try to find an even larger segment. If fit is unsuccessful, the calling routine decreases ke and calls the fit routine again. The first technique presented is based totally on deterministic method. It makes use of quadratic B-spline curve for approximating functions or useful facts. The two-dimensional scheme is primarily based on non-deterministic technique, particularly a genetic set of rules. It has the freedom to utilize any diploma B-spline component. General quadratic and cube fitting. For both the quadratic and cubic cases, the knot vector is constructed as segments are accepted. Double interval knots are used in both cases, producing G quadratic and CL cubic curves. Accumulated chord lengths corresponding to segment boundaries are used for the knot values of quadratic curves. Below equation is used to compute knot for cubic values. U naught is equal to 0, U1 bar is equal to 1. UK bar is equal to UK minus 1 bar plus UK minus 1 minus UK minus 2 bar multiplied by mod of RK minus QK minus 1 by QK minus 1 minus RK minus 1, where K ranges from 2 to n. Local conic approximation. A local conic curve approximation is a technique in mathematics and computer graphics used to approximate a smooth curve in small neighborhood around a given point of conic curve. Conic curves are curves that can be represented as the intersection of plane and cone, and they include circles, ellipses, parabola, and hyperbolas. The local conic curve approximation method involves finding the second order derivative of the curve at a given point, which provide information about the local curvature and the shape of the curve. Based on these derivatives, a conic curve is constructed that approximates the original curve with the local neighborhood. Local rational quadratic curve approximation. We assume points qks to qk lie in a unique plane and that the n tangents ts and te are given. Consider the following figure and assume the moment that r is equal to q of ks plus gamma s ts. R is equal to qke plus gamma e te, where gamma of s greater than 0 and gamma of e is less than 0. Conic approximation is determined in three steps. Interpolate each point qi dash I is equal to ks plus 1 to ke minus 1 with the conic using qks, r and qke as original polygon. This yields the middle weight wi and the corresponding shoulder point coordinate si is equal to wi by 1 plus wi. Computing an approximate conic by averaging the si. S is equal to 1 by ke minus ks minus 1 and summation of si where I ranges from ks plus 1 to ke minus 1. Project each qi into the approximating conic to check if all of them are within the tolerance mentioned. There are three special cases which are handled differently. Ke minus ks is equal to 1. It is there are no interior points. The algorithm computes an interpolating segment between qks and qk exactly as described in section 3.3.3. Ts and te are parallel. If they are parallel to the chord ks, qk and the points qks dash and qk are collinear, then a conic segment is returned which is actually a line segment. Otherwise, no fit is attempted. R is computed, but gamma of s greater than 0, gamma of e less than 0 does not hold. No fit is attempted. Local rational quadratic curve approximation. The figure shows quadratic curve fitting examples of logarithmic spiral. R is equal to 1 by 2 e power theta by 5. In figure 1, we can see that E is equal to 1 by 100 and Kmax is equal to 50. In figure 2, we can see that E is 1 by 1000 and Kmax is equal to 50. Figure 3 depicts the curve when E is 1 by 10 and Kmax is equal to 6. Figure 4 illustrates the curve when E is equal to 1 by 10 and Kmax is equal to 10 in tangent and weights. For each time of fairing, we need three independent functions: tangent rotating P21 2i, point resetting P2i, and weight scaling Ci. Tangent rotating is a function to construct a curvature continuous conic pair by rotating the tangent at the end and resetting two intermediate weights of the conics. To compute how to move the joint uh, and the point P2i along the normal direction at the point, we use the function point resetting. Weight scaling can be used to reduce or remove the curvature extrema within a conic segment by adjusting the weight corresponding to middle control point of the conic CA. If you want to construct an interpolating curve, we can just omit the point moving step in flow algorithm. For a conic spine with inflection points, we can either divide the curve into convex and concave parts and fair every part independently, or fair the whole curvature in uniform procedure, but joint point moving or weight scaling are only applied for two adjacent conic segments or three adjacent segments without inflection. Local cubic curve fitting techniques. We develop fit with cubic. It let P naught is equal to QKS and P3 is equal to QK denote the start and endpoints of cubic Bezier segment, and TS and TE the start and end unit tangents. We must determine the two inner control points P1 and P2, setting the values of P1 and P2 as P1 is equal to P0 plus alpha TS, P2 is equal to P3 plus beta TE. We must determine points for alpha and beta such that the cubic Bezier curve defined by P0, P1, P2, P3 passes within the E tolerance of all Qk, where Ks is less than K and it's less than Ke. If Ke minus Ks is equal to 1, then theoretically any alpha and beta will work. However, they should be chosen so that the derivative magnitudes blend naturally with neighboring magnitudes. Tk is given as Vk by mod of Vk, where Vk is equal to 1 minus alpha k into Qk plus alpha k into Qk plus 1. Using the above equation, reasonable estimates for derivative dks and dke at qks and qke are dk is equal to vks if ks is equal to 0, dj is equal to cj plus 1 minus cj by cj minus 1 into vj, where j is not equal to either 0 or m. J is equal to ks or j is equal to ke. Dke is equal to vke if ke is equal to m. Here, Cj are the accumulated coordinates. Then set alpha is equal to dks by 3 and beta is equal to minus dk by 3. Now assume ke minus ks is greater than 1. Our algorithm consists of three steps. For each k, ks less than k less than ke. Interpolate a cubic Bezier segment to the data p0, ts, qk, and p3, te, thus obtaining ak and pk, the Bezier segments. Ck of u are defined on the normalized interval u e where it belongs to 0 and 1. Average the qks and uh, beta ks to obtain 0 and beta j, where these define the candidate Bezier segment. Check if all qk slash ks less than k less than ke are within e distance of cu. Let p is equal to qk be the point of interpolate and denote by beta bi 3 beta the cubic persistent Bernstein polynomials on U belongs to 0, 1. We write PA as P is equal to B0, 3, P0 plus B1, 3, P1 plus B2, 3, P2 plus B3, 3, P3, where it is equal to P0 of B0, 3 plus B1, 3 plus alpha times ts b1 3 plus beta times te b2 3 plus p3 times b2 3 plus 3 3, and finally p is equal to pc plus alpha ts plus bte, where the point pc is equal to p naught of b0 3 plus b1 3 plus p3 times b2 3 plus b3 3 lies on the line p naught p3, and alpha is equal to a by b1 3, where beta is equal to b by 2 b2 3. From this figure we obtain p by starting at pc, going along a direction parallel to ts for some distance to pd, then continuing from there in the opposite direction of te for another distance. Since ts and te have equal unit length, it follows A is equal to PC into PD mod, B is equal to minus of PDP. Hence, we must compute PC and PD. Then A and B from the above equation are finally alpha and beta. Assume the vectors TS, T, and P0, P3 are not coplanar. It turns out that there is a unique cubic Bezier curve passing through P and PC and PD can be constructed as depicted in figure 1. Let pi be the plane defined by P0, P3 and TS. Intersect pi with the line passing through P and parallel to TE. This yields to PD. Obtain PC by intersecting the lines P0, P3 with the line passing through PD and parallel to TS. We have computed A and B, and now we need to compute alpha and beta, which require a unique value at which the parameter passes through P. PC is equal to gamma P0 plus 1 minus gamma P3, where gamma is equal to PC P3 by P0 P3, which is equal to B03 plus B13. This is quotient of directed distances. The unique constant can be computed using this, which are later useful to calculate the values of alpha and beta. That's it. Thank you. From now, Raja Rohit will continue.
Continuing the topic which Nashket told, we'll see now about the local curve fitting technique error check. When performing local cubic curve fitting techniques, it is a good practice to do some error checking so that we can ensure that the curve meets the desired criteria and is accurate. Some common error checking techniques are visual inspection, residual analysis, goodness of fit measures, and sensitive analysis. In the visual inspection, uh, it is a most easiest and effective method for checking the error in the curve. Here, by plotting the curve with the input points, we can estimate the overall shape. In the residual analysis, we'll be calculating the difference between the input values and the values predicted by the fitting curve. The residual should be small and random with no discernible pattern. In the goodness of fit measures, many statistical measures can be used to evaluate the overall goodness of the fit measures, like mean square error, coefficient of determination, and root squared error on root mean squared error. Using these measures can provide a quantitative assessment of how well the curve fits the input data. Next, we will see about the sensitive analysis. This technique involves testing of how the fitted curve changes when small disturbances are made to the input data. Using this technique, we can identify the regions of input space where the curve may be less accurate or more sensitive to changes in the data. Next, we'll see the planar case. From the previous equations, now we will consider the TS, TE, and P0, P3 are coplanar. Then we get that the previous geometric constructions of PC and PD fails and more than one cubic curve passing through P can exist. Now we take a set of equations that are derived which always yields alpha and beta because there are many special cases in which complicate matters. Initially, a parameter u is assigned to p using chord length parameterization. A good estimation is obtained. First, we'll take u cap of k is equal to 0 and u cap of k is u cap of k minus 1 plus ck minus ck minus 1 by cké minus cks. Here the u cap k are in fact the normalized chord length parameters for the qk. On qks to qke. If p equal to qk, then ks is less than k less than ke, then u cap will be u cap k. Next, we will be computing the tangent Tp at P. So we take S equal to 1 minus U cap and T equal to U cap. By definition, we will get that P is equal to S cube P naught plus 3 square T P1 plus 3S square P2 plus T cube P3. And recalling the de Castel algorithm, we can derive that P0 square equal to S square P0 plus 2S P1 plus T square P2 and P1 square will be S square P1 plus 2S T P2 plus T square P3. Here, P0 square and P1 square lie on the line defined by P and Tp. Next, we get a Tp into P1 square minus P0 square, that is P1 into T square P3 plus T into 2S minus T of P2 plus S into S minus 2T P1 minus S square P0. Substituting P1 equal to P0 plus alpha Ts and P2 equal to P3 plus beta Te, it will yield 3 square T of Ts into alpha plus 3s T square Te beta, which is equal to P minus S cube plus 3 square T P0 minus T cube plus 3s square P3. Next, we get S into S minus 2T Tp into Ts alpha plus T into 2s minus T into Tp plus Te beta, which is equal to 2s into Tp of P0 minus P3. The best way to solve the above two equations so that the special case can be avoided is to use all the previous 6 equations and solve them by least square. Now we should check that alpha is greater than 0 and beta is less than 0. If not, the fit is aborted. This can be solved using alpha equal to 1 by Ke minus Ks minus 1, where alpha I is summation of I from Ks plus 1 to Ke minus 1, and beta is 1 by Ke minus Ks minus 1 of beta I, which is summation of beta I from I equal to Ks plus 1 to Ke minus 1. The Bezier curve is given as P0, P1 equal to P0 plus alpha Ts and P2 equal to P3 plus beta Te. Here Qk is checked if it is within the distance. This can be done using the below formula, that is Qk minus C of U cap of k is equal to modulus of Ck of U cap k minus C of U cap k, that is delta alpha k B1, 3 of U cap k Ts minus beta minus delta beta k P2, 3 U cap k of Te. This formula is less than or equal to E, then Newton iterations are required. Now let's discuss about the fit with cubic algorithm. This code is implemented within the function called fit with cubic. This fits the code segment to set up the input points in the given tolerance E. Here the input parameters are Ks, which is the starting index, Ke, which is the end index, Q, which is array of points, Ts and Te, the tangents at the start and end points, and E will be the tolerance. The output parameters are P1 and P2, which represents the control points of the fitted cubic segment. The function here first checks if there are no interior points to interpolate, that is K minus K equal to 1. K minus Ks is equal to 1, in which case it computes the control points P1 and P2 directly using the equations above. If the points are collinear, that is line is 1, then the function creates a straight line using the midpoint of the segment. If the points are collinear, it iterates through the each iteration points and check if it lies in the plane defined by the start point, end point, and start tangent. If it does, the function uses equations discussed in the previous slides to compute the control points. If not, the function uses a local approximation method to compute the control points. After computing the control points for all interior points, the function averages the values of alpha and beta coefficient from the fitted curve and averages the values of alpha and beta coefficient to obtain the final control points P1 and P2. After that, it checks if the deviation from the fitted curve are within the given tolerance E, using the previous equations. If the deviations are not within the tolerance, the function uses Newton iterations to refine the start value of U and project the point into the curve to obtain the error Ek. If the error Ek is greater than E, the function terminates with an error code. If all errors are within the tolerance, then function returns success. We'll see, as discussed, the fit with cubic function returns 1 for a successful fit and returns 0 for an unsuccessful fit. Now let's see about the examples of planar and non-planar fits. Here for the given diagram, the E value will be 1 by 10 and the K max is equal to 11. And for the figure B, the E is 1 by 10 and K max is 8. And for the figure C, E is 1 by 100 and K max equal to 11. These are just 2D examples. Now, if we consider the 3D examples, for the figure A, the E value is 1 by 10, but the Kmax will be 20. And for the figure B, it's E by 100 is 1 by 100 and Kmax equal to 20. For the given diagram C, here E is 0 and Kmax is 20. Now let's see about different design examples. The first technique that we see is smoothing. Here the below image shows an example of smoothing where the image on the left is the original one and the image on the right is after applying smoothing. This gives the smoother appearance to the polygon objects, whether a surface or a curve. This is used as finishing touch to make it smoother. Next, we see Gordon surfaces. Using this, we can create a surface defined by a series of latitudinal cross-sections and longitudinal cross-sections. This can be basically used in product design. Next, we see surface approximation. Here, the approximation of the surface is done while rendering. The actual mesh structure can be viewed by toggling certain presets in the tool, as you can see in the diagram. Now let's see about the point clouds. Point clouds is a set of points in a 3D space representing surface of a scene or object. Each point here has a location specified in the 3D space and is defined by x, y, z coordinates. These points also have few properties like color, intensity, reflex, which varying on scanning technology used. I'll be discussing it in the Blender tool next. This technique can be used in the different applications like virtual reality, shape analysis, and surface reconstruction. Overall, these points can be used to give rich and detailed representation of an object or scene. This is the Blender tool in which you will be seeing the common surface point clouds. Let me open the tool. This is basically the Blender tool. Here first, we will let's discuss about the Blender tool in basic. It is an open source 3D creation software that can be used for creating a wide range of 3D content, including video games, animations, and visual effects, and many more. It is available on all operating systems like Windows, Mac, and Linux, and offers features such as 3D modeling, texturing, animation, and etc. Blender is used by designers, game developers, and filmmakers around the world, and it has the active community that contributes to it. The Blender user interface consists of several windows, each with its own set of tools and customizations. The main window in the 3D viewpoint, where we can see, view, and manipulate the 3D objects using the X, Y, Z axes. And the interface is highly customizable, allowing us to arrange and resize windows according to the need of the user. Here first we'll see the toolbar on the left of the screen, which have the quick access to commonly used tools such as selection and transformation, property, selection and transformation, and different basic functionalities like rotating, scaling, and transformation and annotation. And on the right, we can see the access to settings and parameters for the selected object. It also features wide range of menus and shortcut keys for quickly accessing various functions. For the point cloud visualizer, first we should install an add-on called SpaceView 3D Point Cloud Visualizer. We can add it from the edit screen, and when we go to preferences, we'll be finding it under the add-ons. As you can see here, I've actually added it. Next, we need to get the 3D model, the point model cloud for the visualization. Before loading it, first we should create an empty object because there should be at least one basic object so that the point cloud visualization can be observed. We can add that empty object in the use object mode. And when we click on add and click on empty, we can add a plain axis. I've already added that empty object here. Next, we should load the 3D model. We can load it by taking the location of that PLY file and opening it here, and when we click on draw, the point cloud visualizer will load the 3D point visualization tool. Here we can observe that we can see this whole 3D model in different axes based on our requirement. This makes easy for the user to develop and make changes to it, and we can easily manipulate the point cloud with the entry point. Now let's see some basic properties which can be used. Here on right side we can see we have different properties like display, which when we change we can observe the changes in here, and we can also change the pixel size of each point, making them more versatile. We can even change the alphacity of the whole body using the alpha setting, and then we can use the illumination tool to illuminate in different shades using this. See, as you can see, when I move it, 1 second, yeah. See, based on the moment, the shadow and everything is managed here, and we can do different techniques for like different changes to it by using depth filter, and we can use event clip, which can be used to take only certain part of the uh, whole 3D visualization, and so that we can easily manipulate if there are any changes to it, and we can edit it in the edit mode. We can even filter out different parameters using it, and we can render a part of it and make them and use them for the different opportunities, use them in different places by rendering it. We can even while rendering, instead of rendering the whole 3D model, we can also render the part of a model so that based on the requirement, uh, we can use it. And this is the basic 3D point cloud visualization. And thank you.